Okay.
Alright, so as some of you may have guessed by this point, today we are going to talk about the broad phase of collision detection. Now, broad phase covers all those techniques, which are a very wide set of techniques, for reducing the number of pairs of shapes of bodies that you run the precise SAT collision detection over. So if you have lots of shapes and you have to run the SAT collision detection between every pair of those shapes, then, well, your engine is probably going to support something like 10 or 20 of those at a crawl. Okay? Of course, unless you really need to have them all colliding together, which is kind of an unrealistic scenario, most of those pairs of shapes will be too far away to even consider them. So what we do with broad phase collision detection is indeed we try to, as early as we can, remove checks. So we do not perform checks. Now, so we will talk about, well, indeed, the more traditional concept of broad phase collision detection. Then we'll talk about bounding spheres. Remember that their objects are moving, and especially for the broad phase, then yeah, considering their movement may be useful. Then we'll talk about ways to do space partitioning. Then we'll talk about bounding boxes, aligned and non-aligned, and all the ways we can optimize collision detection for boxes. Then we'll talk about further optimizations, such as islands. And then, yes, indeed, we'll introduce the current assignment. Now, first of all, well, yeah, this is a bit of a pop quiz. But what is the fastest instruction ever in life? Close enough, but there's one that's even faster. Yes. The one you do not run. So computations you do not perform are absolutely the fastest of all. Okay? They take literally no time whatsoever. So if you can manage to compute less stuff, then, well, your application is going to be fast. If all you compute is what you really need to compute, so what really gives a response, what really changes the state of the world in some manner, then your program is going to be exactly the same, but faster. Kind of obviously. So the idea for a collision detection system is indeed to quickly and cheaply, if this process is not cheaper than the SAT collision detection that it saves, of course it's pointless. So we're replacing SAT with something that's heavier to avoid SAT. So definitely, the fact that these algorithms have to be very cheap and very simple is at the core of their nature. And this process is known as collision culling. You know what culling is? First one culling? Raise your hand with enthusiasm if you know what collision culling or first one culling is. Seriously, come on. So, you haven't seen first one culling in the first year? Really?
No, you practically don't do anything with graphics in the first year.
That's impressive. Okay. Anyway, the idea of culling is to reduce the set of things you work on. When you're doing graphics, when you're doing rendering, objects which are outside of the screen, you do not care about rendering them. It's a waste of time, obviously. So, first-time culling means that and its bigger brother occlusion culling mean that you do not send to the rendering pipeline objects which you are certain will not appear on the screen. Collision culling is the very same thing. So we try to find all those pairs of objects which cannot possibly collide. Like objects in, I don't know, different rooms in the game world, or objects which are so far away that it doesn't make any sense to think that they might collide. This process is, indeed, the idea of the broad phase is that it doesn't tell us precise information, like these two objects are colliding here. It only ensures lack of collision. So it doesn't give us any positive information. It gives us very early negative information, like these two objects are so far away that they will not collide, so don't go any further, okay? The presence of collision, so the precise positive information, will only come during the narrow phase, okay? So is it clear what we're doing? We're removing big pieces of uninteresting possible computations, alright? Now, the easiest way of doing collision culling is what you were talking about as broad phase. So you use some simpler shapes, like bounding spheres, which are very fast to check against other spheres, and which behave very nicely with respect to rotation, and use and check before doing SAT. You check if the sphere that contains the object is colliding with the sphere that contains the other object. Do you know what bounding spheres are? Who knows? Okay, very good. So you can imagine, right? The sphere is a very simple shape, and what happens to a bounding sphere when an object rotates?
Nothing.
What's the bounding sphere of a rotating object? It is the exact same, right? If you have a sphere that contains an object, it doesn't matter how much the object rotates. So, if, I don't know, you have a car, I don't know why I try to draw stuff.
Or is it just small?
Yeah, come on, this is... Okay, no, it's not for me. And you have a bounding oval. Imagine that's a bounding sphere, right? Even if the car is turning, rotating, etc., it is still going to remain in the bounding sphere, because the bounding sphere finds the biggest extent along any direction of the object, and then that is the maximum. Even if the object rotates, the maximum extent is obviously not going to change, alright? And when the object moves around, the bounding sphere obviously moves around with the object. So if the object is translated, yeah.
If the object is not has a set point on its center, then you have a problem.
What is a center? Center of geometry or center of mass? They don't need to be the
Center
same.
of geometry.
So?
When you calculate the sphere is going all the way
Oh yeah, the original mesh has to be
at the center.
at the center, of course. Yeah, center of geometry has to be the origin when you compute the bounding sphere. Otherwise, yeah, it kind of doesn't make any sense. Yeah, okay, or if this is the origin and your object is here,
Yeah.
then the bounding sphere is going to come out, well,
Or even worse.
or,
It's like-
oh yeah, actually, yes, maybe even worse.
Yes,
Yeah,
that's-
yeah. But
that's-
okay, come on, you should be able to see that during debugging that something is wrong. So draw your bounding spheres before relying on them. Okay, so, well, first of all, how do we represent two bounding spheres? How do we represent a bounding sphere? No, you guys don't answer. Yes.
Radius.
Yes. And? Origin. And an origin? Because the center of geometry may not necessarily be the center of mass or center of geometry of the object itself. I mean, you could have a bounding sphere that's slightly skewed for whatever reason. But in general, you have an SD, but yeah, even if, or actually, yeah, it makes always sense to have the sphere, the bounding sphere at the center of the geometry of the object. So, but when the object moves, of course, the center of the sphere becomes the translated center of geometry of the object. So, a sphere is indeed a point, a center, and a radius. When do we have an intersection between two spheres? Come on. Yes?
Distance between the centers is smaller than the combined radius.
Then the sum of the radii. Yes, absolutely. So when the distance between the center is smaller, the center is smaller than the sum of the radii. Now the distance between 2 points requires, unfortunately, a very evil and unlikable operation, which is a square root. Now, do you like expensive operations in games? No, you don't. No one does. But fortunately for us, we can actually just square both sides of this formula, and the formula remains perfectly valid. So what we can do is we can take the squared distance between the two spheres, which is simply the distance without computing the square root. So it's much faster. It's a bunch of sums and multiplications, and this has to be smaller than the sum of the radii squared. Okay? These two things are exactly the same, of course. So yeah, you can use whichever you want. If for you it makes more sense to use this one, of course you can, but this one is going to be slightly faster to compute for lots of spheres. Okay, unfortunately, our spheres are going to be moving, right? How would you handle the case of moving spheres?
Well, you can increase their radii by their speed.
You could increase the radii by the speed. This is actually Yeah. Well, it's like the second time ever since someone answered with the answer on the slide. So come on, this is a historical moment. Yeah, absolutely. So the point is that if the objects are moving, then they are going to intersect sooner. So it is like two still objects with a bigger radius, right? So the objects are moving, and the fact that they're moving during this frame means that they are essentially, for all practical purposes, bigger objects. But how much? How much do the radii need to be increased? It depends on the speed, of course. But so, is the increase going to be bigger for objects that are going towards one another, or if one object is going away from the other? In which case is the collision more likely? So in which case is the radius that we check against going to be bigger? He says when the objects are going towards each other. Who votes for this answer? Who votes for the other one? Why would you vote for the other one?
Well, the problem what I see is that if you want to know which ones are moving towards each other, you have to start doing checks and everything like that.
What checks?
Well, you probably have to figure out which direction they are going, and if two objects that you are comparing are indeed going closer to each other. So,
but if they are going closer to each other, then it means that their likelihood of intercepting each other is going to be greater.
Yeah.
So their radiuses are going to be bigger. So if the radii are bigger, then the chances of collision are bigger. And if the radii are smaller, then the chances of collision are smaller. Now, the same reasoning applies to the fact that if they're going towards each other, then chances of collision are higher. And if they're going against each other, away from each other, then chances of collision are slower. So we have to correlate the size of the radii with the chances of collision.
How do you do that when you have, for example, you have 500 objects in your scene and all moving in different directions and everything?
Oh, we're just talking about pairs of objects here.
Oh, just pairs of objects?
Yeah, exactly.
Okay.
We're just talking about pairs of bounding spheres. So you're about to do an SAT check, and you want to decide if it's really necessary. Just a pair of objects. So for the moment, we're just talking about the case of every pair of objects.
Basically one step on
Exactly.
top of the...
This can already save you lots of work, because of course the sphere check is going to be much faster than SAT. Especially because failing SAT, so determining whether the objects are not colliding with SAT requires you to check all the x's. So it is the slowest case. Alright? But in general, no, this is the case where the radii will have to grow bigger. And, well, so, of course, instead of working with two velocities, we can collapse the thing to just one velocity, of course. So we can just think in terms of relative velocity. And relative velocity is... velocity between the two objects. How do we compute it?
Subtracting one from
You
another.
subtract the two velocities. So that becomes the velocity of just one of the bodies, which incorporates the velocities of both of them. Alright, so we take the relative speed, which is the difference between the two velocities, and we dot this speed by the direction, the axis that connects the two centers. So we have the axis between the direction between the two centers, and we see if the velocity is actually making them go closer or further away. And this is sigma, which is the relative speed, so not the relative velocity. Sigma is just a number that says how much the two spheres are getting, the two centers of spheres are getting closer. So we're ignoring all the components of movement which are perpendicular to the direction of the spheres, to the radius. So if we have velocity like this is the line that connects the two centers. Now this velocity doesn't influence the collision detection. It doesn't influence anything because it's perpendicular. So it doesn't make the objects get closer or further away. So we don't care. Alright? And indeed in that case the dot product is going to be 0. Yep.
when objects are moving away from each other, can you assume at that point that you are not going to do any collision, or do you still have to check?
You should probably still do the check, because unless you can guarantee that you're running collision response and everything is going to be correct, then you should still do the check with the still objects, because you could have colliding objects that start to move away from each other, and so they still need to do collision detection. But so in general, you could also see that if this dot product is negative, you take sigma to be 0, and you just do the regular check. Alright?
Yep.
And then when you check the distances between the centers, the distance has to be smaller than the sum of the radii plus the relative speed, because that is how much the objects are getting closer to each other. You with me so far?
Yes.
Good. So, oh yes, there's another piece of art here. So the idea is that if you have, this is actually I think a reasonable way to represent things. So you have the two spheres. The two blue spheres originally were very small, but the sphere on the left is moving very, very fast. And it's moving so fast that, we actually consider the sphere to be much bigger. But we only consider its movement towards the other. So maybe the velocity of this sphere was something like this. But we are projecting the velocity along the axis that connects the two centers. Alright? Because of course, it doesn't make any sense. We could potentially just take the length of the relative velocity. But the length of the relative velocity is much bigger than the projective velocity. In general, it is bigger than the projective velocity. So instead of projecting the whole, of using the whole relative velocity, we just take the relevant part of the relative velocity. Alright. So, already having this can improve if you have lots of objects, and maybe these objects are distributed uniformly across your level, so they are not so close to each other. They do not collide every time. Even if you have lots of objects, this already will make your collision system noticeably faster. Very much, because of course doing a square distance between two vectors is almost doesn't have any cost compared to the hundreds or thousands of checks that you have to do for a failed SAT. Because remember, when you have distant objects, SAT fails. It says there is no collision. But to fail, it has to check all the faces and all the cross products between the edges.
Also, this space is really good to parallelize, like really easy to parallelize.
Yes, and this thing can also be run in parallel very much, absolutely. Which is, actually, bins are one of the ways you use to do the check in parallel, absolutely. So, imagine though, you have a very, very, very big level, okay? Imagine this level is gigantic, right? Kilometers and kilometers of level, okay? Now, does it really make sense to even do the sphere-to-sphere check? So, or actually even better, so far, even if the even if the sphere collision check is fast, and let's say you have 100 objects, how many sphere-to-sphere checks will you have to do? You have 100 objects. How many sphere-to-sphere collision checks will you have to do? No, you guys are answering. Are you a second year? Okay. But no, you're not entitled to answer. I want an answer from, go ahead. The square, alright? So, is a squared computation something that we really want? No, because you add a new object in some room, or you add, I don't know, 10 objects in a room, and suddenly all these new objects make everything much, much slower, right? They multiply against everything else. So this is something we really do not want, especially because unless you put all the objects together, like a pen full of plastic balls, okay, which you can arguably build a game around, then you don't care about these many checks. So one of the ways to do this is to partition your level or your game world into containers, bins, which are very simple in terms of geometric shape and which contain lots of objects. And then you do collision detection only between pairs of objects which are in the same bin. Absolutely. You can actually shout something like that. Oh, no. Alright, so the idea is that and an object can fall in multiple bins, obviously, in all the bins that it touches. And so, what are the collisions that we're going to do? Are we ever going to check F against B? No. Are we ever going to check A against H or F? No. Are we going to check E against F?
Yes.
And E against G?
Yep.
Alright, so roughly, the more bins you have, the less checks you're going to make. And how much does it really cost? Imagine you have the bins already. How many checks are we going to make? Well, most certainly not a squared number, right? Or at least it's going to be squared, but in the number of spheres, of objects that fall in a bin, which is far, far less. It's usually, on average, you will expect that, yeah, your objects will fall uniformly in the bins. So now you can say that if you have k bins and n objects, now the number of checks you'll perform is going to be n divided by k, which is the average number of objects you get per bin, squared. Alright? Which is far, far, far less, especially because you can have as many bins as you want. So you can have plenty of bins. You can ideally, well, okay, a bin for a pair of objects is obviously excessive, but you can have a bin for 4, 5, 10 objects, which is fine. You can do all the checks, the sphere checks you want between 10 and 10 objects. You cannot do that for 100 or 1,000 objects, alright? And when you have the bins, you do nothing. The bins is a list of bounding spheres. It's a list of bodies. So you just have the list of bodies and you just do the check. You don't have to do anything else. Yes?
Isn't it n minus 1? Which doesn't check anything.
Oh, come on. Yeah, but this is the complexity. Oh my god, I didn't know I had computer science purists here. So O over n k over n divided by k squared. Now it's correct. Okay. Well, how do we partition space into bins? Well, first of all, we can do the sphere. Every bin is an axis line bounding box, right? So the check is very, very simple. You simply see if for every side of the bounding box your sphere is inside or your sphere intersects. So if the linear distance across every axis between the center of the sphere and the lower and the upper bound of the bounding sphere is smaller than the radius plus the relative velocity towards the center of the bounding box. Yeah.
Okay. Do you normally optimize that so you can just basically keep on checking the planes on one side until you find the one that it's not behind, and then the one for the y-axis and the z-axis?
This is just clipping, but you know that the planes are aligned with the axis. So this is just a check of a coordinate of the. So you just take a coordinate, Cj, of the center. So J actually stands for an axis. So you can have Cx, Cy, Cz, and you check against the lower bound of the bounding box over x over y over z. If your x is much smaller than the lower x of the bounding box, then you're out. If your x is much bigger than the upper x of the bounding box, then you're out, and so on. And you stop as soon as you find a single axis with respect to which you're either too much lower or too much bigger.
Right.
Okay?
Yeah.
That's it. But this is a super cheap test. I mean, you do 3 plus 3 checks for every bounding, for every sphere. No squares, nothing whatsoever, because you're talking about linear distance along an axis, which is just the difference between the coordinates. Okay, can we do faster? Oh, yeah, wait a second. Oh, yeah, it's here. So, no, I'm not going to show the slides now. Can we do faster? Do you think there's a better way to do this? Because if we do it this way, how many checks do we have to do to partition the spheres into the bins? We have n spheres and k bins. How many checks are we doing?
N times k.
I hear n times k.
Times 3. Because
That is absorbed by the...
times k divided by 2.
Yeah, that's fine. The divide by 2 is a constant factor, so we don't care. But it is, yes, n times k. Because for every bin, you have to check all the spheres. Yeah, you could argue, yeah, but whenever I find that a sphere is in a bin, then I don't check it against all the others. I just check it with the neighbors and put a sphere in its bin and possibly in its neighbors, because a sphere may be like E. You have to, when E falls into, I don't know, this one, you still have to check if you have to also put it in the neighboring bins, but that's fine. But in general, N times A. And if you have a lot of bins, then this actually becomes expensive. Pointlessly expensive, yes.
You could have information of the bin if it is actually having energy in it. If they don't have energy in it, the state can be disabled.
Oh, wait a second, yes, that's called islands, and we are getting there. Just be a bit patient, but yes, that is exactly one of the things we do. But wait a second, we want to put spheres into bins, and we want to do this as fast as we can. Imagine that the bins are all of the same size, alright? How would you say, okay, yeah, go ahead.
Always half the bins, start with the full screen first, or the full...
You can go even faster. Yes, you're talking about a binary search, and then you can do that. But if the bins are all the same size, you can be even faster. No, no one answers from 30 years. Not yet. Come on, guys. Give room to the new generations. Come on, new generations. Defend your honor. Okay, I really need to find a way to erase this thing.
Just do it like Dino and flip it behind the whiteboard.
Oh yeah.
Seriously, yeah, can you do that?
Or just throw it behind it.
Throw it.
Throw it.
This really doesn't feel like an optimal solution.
Now get it back from there.
Well,
I could actually just keep it like this. Wait a second, but we do have two of those. We might actually try. Okay, anyway. So, you have a bunch of bins. And this is a matrix of bins, or a 2D array, or however you want to call it. Alright? Now, you have a point, which is usually the center of a sphere, like this point. Alright? Oh, the bins are all wide W and tall H. Same applies for Z. In this case, Z actually just behaves like the width and height, so it's like the only case you'll find in physics. So every bin is big W times H. And even easier, this is the origin. And you have this point, it's X, Y. Now, the question is, I want to find out that a sphere here, this point here, center of the sphere, goes into bin 0, 1, 2, 0, 1, 2. Okay? So I want to find a way to go from X, Y into 2, 2. Or IJ, which are the indices of the bin. Go, unleash your imagination. No, you can't answer. Yes.
Divide the growth coordinate by the bin size.
Yes.
And then you get the bin coordinate.
When you get the bin coordinate?
Yeah, the indexes of the x and y index of I and j.
Very good. So, the suggestion, suppose that's what you wanted to say, is that I is going to be equal to, well, just with a bit of care, round of x divided by w. And j is equal to the rounding of y divided by h. Now, the rounding is actually important because, well, you want to find the bin that you're the closest to. And also because the indices are integer numbers. Whereas the division gives you, yeah, back rows. The division of x divided by w is a floating point number, okay, but you need an integer, so you need to convert somehow, alright? You can round or... No, actually you shouldn't round, you should probably just do a floor. Alright. Now, how long does it take to perform this check? Yep.
Well, I think quite long, because you're doing two divides.
So, all right. Now, how many checks did we do before? Previous algorithm, right?
7,000.
It was n times k, right? Plus then n divided by k squared. This is the final number is going to be proportional to this. Okay. Now this is the same. This just depends. This doesn't depend on how we build the bins. So building the bins before required n times k operations. Alright? Which are a bunch of checks, no divisions. Division between floating point numbers is significantly slower than sums and multiplication. So you are onto something. How many checks do we perform here? To determine which balls, which spheres go into each bin. We do perform something. How many checks do we perform? No, you guys can't answer.
Shut the fuck up, Thomas.
Yes?
First cell checks for the width and the height. Then if you found one, then it just puts in there and
So, sorry, say again.
He checks for every cell that hits in the width.
For every cell?
In the thingy.
Yeah, let's try to get a number. So, the thing we want to know is how many checks against spheres and bins do we perform with an algorithm like this one?
I think only the elements you have and
Only the n. Which one is bigger? How many cells do you want to have in your game? If you have lots of cells, each cell, each bin will have less spheres, which will mean less collisions between pairs of spheres. If you have tiny cells, then every cell is going to intersect lots of spheres. So yeah, you have to find a balance, but in general, K is going to be big. Especially if you're talking about a very big level, then K is going to be big. But even worse, wait a second, what if we have a gigantic level? Open world, okay? Huge level, okay? With lots of objects very far away. Then you need to have lots of bins, right? Every bin could be, I don't know, a region, a small region in a gigantic world. So you could have millions of bins. In this case, this becomes not trackable. Not in the game. You can obviously compute the result, but it's going to be too slow. But in this case, you're just checking the number of spheres. You just put every sphere in its bin, and that's it. And actually, if you start with an empty list of bins, and whenever you put a sphere in a bin, you add the bin to the set of bins which contains something, then you can very, very quickly find a set of bins which you actually have to check. So, you start with an empty list, whenever you put something in a bin, you add the index of the bin into the list. Oh, sorry. And at this point, you have the list of all the bins that contain something. So even if you have lots of empty bins, you can even directly skip computing anything about them. So this algorithm not only becomes very fast, but it also allows you to ignore all the bins which do not contain anything, which is an added bonus, which is a significant one, because then you don't even have to run through all the bins. If you have a very big level with lots of empty bins, you ignore them right away. Yes, now?
You can need a bin list with 2 objects then, right?
Sorry?
A list with bins that only have 2 objects because one...
Oh, yes, you can be even more refined, of course. Yes. Whenever you add something, and to avoid adding the same bin more than once, you actually only add a bin when it goes to 2 objects. Yes, absolutely. Yes.
You also need to check the neighbors when you put something in a bin.
Yes, of course.
And
But
make sure that the object is not bigger than the size of the bin.
Yeah, of course, obviously. Or otherwise, you can put the object in a lot of bins.
True, but then you have to know a lot of checks.
Yeah, of course. That's why the bins don't have to be too small, because otherwise a bin risks intercepting plenty of objects. So yeah, there is a bit of an art there, obviously. It's in that case, you can have multiple grids of bins, depending on the rough size of the object. So very big objects go into very big bins, very small objects go into very small bins, and you have like 2 or 3 kinds of bins. Right? Okay, so if you do this, then you have optimized for sparsity And this is a very powerful way. So does this answer actually your original question? So you see, the point of the growth phase is to optimize the interactions between all the objects as a whole, not just pairs of objects. So yes, the growth phase also covers that. But more importantly, when you have lots of objects, to find just subsets, because the bins are... Oh yeah, that was going to happen. Because the bins... No. Okay. Yes. Okay, so the bins are essentially a set of objects that interact with each other. Alright? Now be careful, because there can be a very evil case that presents itself, which is a bit tricky. Is the bin the only unit that we care about? No. The answer is absolutely not. Because you can have a horrible case like this. But you can. You have to do what's called a flood fill of the bins to find all the bins that share relationships of this kind. And be careful. So absolutely remember that before you run the collision response, you have to make sure that there doesn't exist a path of collisions between objects. You can still use the bins, of course, to just determine which objects you have to run the boundary sphere collision detection, obviously. But after you've done that, remember that you'll have to connect all the possible chains of collisions together. So this is all bookkeeping. This is not particularly hard, but so remember. So the broad phase is still going to be the same, but after the broad phase, you'll have to reconstruct the groups of objects that interact with each other. Okay, now... Oh yeah, absolutely. Yeah, let's say we take a break. So, guys, shall we get started again? There is another very elegant algorithm for collision detection between axis-aligned bounding boxes, which results in a similar response as the one we got from the previous algorithm, but, well, it is a slightly different algorithm in some sense, and it can be used in conjunction with the previous one. This is more useful for what we could, yeah?
Can I ask a question about space collision?
Yes, of
What
course.
do you do with moving objects?
There's a sigma there.
Yeah, but do you like
Sigma
place
is
them in bins every tick, or do you keep track?
oh yeah, an object that moves goes out of bins and into bins again.
You don't keep it in the bin and you check if it's still in.
You can, but if you do the modulus thing that we saw before, then it's faster. It's as fast to determine what bin you're in or to do the check. Because if the check fails, then you have to find a bin. Or so yeah. So the check is so fast that yeah, with the hashing you don't need to do anything else. Oh, and yes, so I was discussing with you. There's also something nicer that you can do if you don't want, if most of your bins end up empty, which can be the case if you have a very big level, but stuff moves into the level. So some bins are going to be empty. You can actually do a modulus operation. So you can have less bins stored than you have in the world. You know what a modulus is?
Yep.
So basically you have your bins wrap around. You just have fewer bins and they wrap around. So bin 10 goes back to being bin 0. So you will have some checks between objects which are very far away but ended up in the same bin anyway because you did the modulus. But the end result is still going to be very fast. Is the idea clear? Who doesn't find it clear? Alright, so oh, this is okay. So
You can do it!
imagine your game world is really big, right? We're talking about 1,000 kilometers by 100, okay? huge work. And for some reason, we really want to store it all at the same time. And, well, the size of your bins is this. Okay? That is a small bin, so you will probably need lots of bins, right? But in your game world, in some areas, at some times, nothing whatsoever happens, right? So you have empty areas and areas with lots of stuff. So one may say, okay, we want to have far less bins. Something like this, right? A very small grid. Now this is probably too small, but imagine you have a very small grid. How can we make this work? We just keep a small grid for a much bigger surface, for a much bigger volume if we're working in 3D. Okay, yeah, you can ask, no, wait a second, you're a third year. Come on, think about it. So my suggestion before was we wrap stuff around. So, okay, go ahead.
Can't you just group objects together and then make them separate things?
It's more elegant and battle-tested solution that we can find. Come on. Just try. Don't be shy. So I will actually give you the final formula. Let's say our size. So we would have like 10,000 bins on this side, but we actually just have k. Okay. So we just have kx bins.
Use power of 2's.
And ky bins. Sorry.
Use power of 2's.
No, I won't. This is a game word. It's in meters. So we have kx and ky. So what we do is we compute the index of a bin, which is going to be the x of the object divided by the width of the bin, modulus kx. What does this mean? No. Yes?
That you actually repeat the bin for each time.
Yeah.
But what if you have like 3 of those bins next to each other and one of the cells, which are the same for each 3, all contain an object?
Then those objects will fall in the same bin.
They will also get tested for each other.
And they will get tested, but then the test is going to determine that they didn't collide.
Yeah.
But if kx and ky are big enough, then this will not happen so much. And what you will get is that you will get less empty bins.
Yeah.
Alright? So what you do is basically, what you're doing is you're taking this bin here, this is a physical bin, a bin that you're actually memorizing, and this bin is covering for this bin here, this bin here, this bin here, this bin here, and so on, right? It's also covering for this bin here, and so on. So every bin that you store is actually covering for a long list of, you can imagine virtual bins. If you know how a cache works, people who know how a cache works, which I assume...
Hey, we're not supposed to answer.
Not allowed.
This is exactly how a cache works. So what you're doing is you're using something smaller to represent something much bigger, but the smaller thing is more relevant. And if your bins are, if you only generate objects around the player, then this is going to be even more effective. Because if you generate only stuff around the player, and everything else is kind of put to sleep, where you don't run physics on objects which are too far away, then this becomes even more effective. Because then this becomes an actual cache of what's happening around the player. But this becomes relatively advanced relatively soon. So just be aware that this stuff exists in case you ever need to really run this stuff. Okay, now, so imagine we have our wonderful bin-based algorithm. But now we, well, yeah?
Why wouldn't you just increase the size of the bins and then just cover the whole area in smaller?
Because very big bins will contain lots of stuff.
Yeah, but it's the same with the modulus. I mean, if you have like
Yes, absolutely. It depends on the way your objects are distributed across along the game world. But especially this becomes extremely relevant if indeed you have mostly objects around the player. So if you spawn smaller objects on your own player, which is a very common scenario, then in that case, having bigger bins will make lots of small objects put together. Whereas if you have the wrapping bins, then a bin will still contain on average the same number of the same small number of objects. So bigger bins ensures that you will have lots of objects in a bin. Whereas, well, smaller.
More evenly divided.
Sorry?
It's evenly divided.
Yeah. But you can try, you can profile it, you can play with these things. It depends on the size, on the shape of the board, and the distribution of objects. Yeah.
Do you refill the bins every frame?
It's fast enough that it's actually convenient to refill the bins every frame. Yes, absolutely. Especially with the sparsity check that we said before of storing which bins get to at least 2 objects. Then yeah, so you will still have to do, you cannot ever do less than a pass of all your objects in a frame. You have at least to draw them. So as long as we stay in the confines of doing just a single pass of the objects, then you're fine. Alright? Cool. Do we want very small bins? No, so our bins ideally will contain a few objects, 5, 10, 20 objects. Okay? 2 small bins risks making big objects very problematic. So what we discuss now is how do we handle a reasonably sized group of objects all in the same bin. How do we handle them to even quicker? So we keep refining our check. We keep adding intermediate steps until we get to the perfect balance. You could also have relatively big bins and then have something more refined inside each bin to further determine which checks you really have to perform. It's clear what we're going to do. So right now we're going to add another layer of checks inside the bin. So inside every bin we are going to do another check to see which objects actually collide inside the bin itself. Right? We have a bunch of objects in the bin. We don't want to check every object in the bin against every other object in the same bin. But we can keep adding refined checks. Of course, if you have too many layers, then at some point it becomes pointless. There is a simple and powerful algorithm for determining groups of intersections. This algorithm is based on the axis line bounding boxes of your objects, not on the spheres. You can trivially build an axis line bounding box out of a sphere, or you can build the axis line bounding box just by itself. And this algorithm is not only particularly fast, but it's also particularly useful when the axis line bounding boxes do not move much. They can move, but not too much, like one goes here, one goes here. They all move like crazy across frames. The idea is that, well, first of all, you update the axis line bounding boxes if needed, because remember that you still can find the extent with your SAT system can give you the extent of an object along a separating direction, and you can use the 3 extents to compute the bounding box right now in a more precise manner, if you have a fast way of doing so. Then you do an insertion sort of all the extreme points of all the bounding boxes along every axis. So if you're working in 2D, then you sort all the extremes of all the bounding boxes, so the start and the end points, in a list. By X, and then by Y on another list, and by Z on another list. You know what insertion sort is? So basically, the idea is that you take a point, and if its neighbors are not one smaller and one bigger, you move it forward or backward until it gets to its point, right? So obviously this algorithm is going to be very fast if the list is almost sorted. So if the objects do not change too much, then of course you will have to do very few steps to find the right place for an object, because the right place for an object in the list is going to be close enough to where the point started. So after the first frame, the list is nearly sorted. This means that we just do basically a single pass of the list. It's not a full sorting. And it takes, well, O of n, so it just takes one linear pass of all the objects. At this point, we run the so-called sweep algorithm. So this is the sweep phase that you will find in plenty of physics engines. You start with a set of active intervals, which is an empty set. When you find a point which was the beginning, the lower side of a bounding box, you add it to the active set. When you find a closing point, so the point where a bounding box ended, you remove it from the active intervals. Oh, of course, when a beginning value is encountered, you add it as a box that intersects with all the boxes which are currently in the active set, right? So you sweep the list of sorted extremes. When a new box enters, it collides with all the things the boxes that are open at the moment. When a bounding box is closed, you remove from the set of active bounding boxes. Can you figure this? So, this is kind of fun. Alright, so we have these boxes, and we'll just think about their x. Alright? So just along the x. So, the points are, sorted points are A, B, C, D, E, F, G, H. Alright. So, at the beginning, the active set is empty. Right? So, active set doesn't contain anything. We encounter A. Oh, wait a second. This is 1, this is 2, this is 3, this is 4. The numbers don't need to be sorted. These are just the IDs, the identifiers of the boxes. So, we encounter A. A is a beginning of a box, right?
Yeah.
Guys? Yes. Okay, so A is the beginning of a box. So, we add the corresponding box to the active set. So, the active set now contains 1. What's the next point we find?
B.
B. B is an opening point, right? So, we add the corresponding box 2 to the active set, and we mark 2 as intersecting with all the boxes which are currently in the active set. Because you have an open box and another open box, and clearly they are intersecting because they're both open. If they're both open, you haven't found the end. So yeah, they do share some area. So the intersections now contains 1, 2. So we add it to the intersections. Yes?
That's on the intersection of the x-axis, right?
Yeah, absolutely. Then we'll see how to do it with the other axis. Yes. Good eye. Now, next point is
C.
C. C is an opening. So, what happens?
Add 3 to the x.
Shh. What happens? Yes?
You add 3 to the active set, and then you have an intersection between 1 and 3, and 2 and 3.
Very good. 3 to 1, and 3 and 2. Alright? Okay. Next point? D. Next point is D. Oh, D is a closing point. What do we do? Yeah, guys, you can answer now. You remove 2 from the active set. 2 is over. The interval of 2 is over. So 2 doesn't intersect with anything else. So we remove it from the active set. Is it clear, or do we have to finish? It is clear. Now, whenever the idea is that you do this for every axis, and then you intersect the results. So, if you have an intersection along the x-axis, but not along the y-axis, then the boxes are not intersecting, which is the case for all of these, right? So the idea is that you run the sweep algorithm for every box, and then, for every axis, and then you intersect the results. Now, of course, you can play with this. You don't need to run the sweep against everything. You can just, you can just run it on the things that intersect. But in general, the idea is that you have a very fast way to find the possible intersections along an axis with this algorithm. And you can run it on all the axes, and then intersect the results together. Alright? The most important thing is that to have an intersection, then the intersection has to be true over all the axes. Alright? So basically, by doing just one linear run for every axis, you get to find all the possible intersections of a set of objects which are probably colliding with each other. So this algorithm works very well, unlike the bins, which are very good for finding groups of objects which are very far away and which will never intersect. This is a very good way of finding intersections between objects that probably intersect with each other. So this is a very good thing to do inside a single room or inside a single bin, where you have objects which are moving a lot and colliding a lot with each other. Yes?
So actually this one is more like the middle step.
This is what you could call a middle step. Absolutely, yes. Because if you think about it, well, doing the sorting step and doing the 3 axes is more expensive than just the regular bins, right? But when you have stuff that actually intersects, then the bins kind of become useless, because if you have stuff that's very close together, then the bins do not disambiguate anything. So yeah, you can consider this to be essentially a middle step, absolutely. Alright, now, the second middle step is oriented bounding boxes, especially if you have more complex shapes. So far you have probably said who managed to get SAT working? At least SAT, not the context manifold determination. Yeah, raise your hand. Don't be afraid. Okay, enough of you. So when you're doing separating axis test, you can add some sort of middle phase to narrow phase optimization. We're going down towards SAT itself. You can do an optimization to test far less edges and normals. If you think about it, how many tests are we doing between two boxes when we're doing SAT? What tests do we do? Yeah, the answer is there actually. But why do we do that many tests? SAT, we take every normal of every face of one body and we check against the vertices of the other one. Then we take every normal of the other body and we use that as a possible separating direction. Then we take every pair of edges, right? And we do the cross product between the pair of edges and we use that as a separating test. So for boxes, what happens is that we have 6 face normals, 6 face normals, and then 12 edges squared. So the total number of tests become 144 plus 12, which is 156 tests for something as stupidly small as a box, right? That's kind of a pity. Let's draw a box. So, this is a box. Yeah. And this is another box, right? Now, the cross, let's think about the cross products between the edges, right? Let's consider these edges here, A1, B1, C1, D1, and then let's consider these edges here, A2, B2, oh no, sorry, oh yeah, C2 and D2, alright? What was the test that we said we do the edges? Come on, 30 seconds is not a justification for days. So what tests do we do between the pairs of edges? I say it out loud, don't be afraid. Cross product. Right. We do the cross product between every pair of edges, and we use that as a possible separating axis. All right. So we will do A1 cross A2, B1 cross A2, C1 cross A2, D1 cross A2. Now, there is something very important that you have to look here. This is extremely important. Before we proceed, there is actually a bit of philosophical importance to this. Keep your eyes open, because there is plenty of ways to find hidden optimization opportunities taking advantage of symmetries. Symmetry is a core concept in anything scientific, in development as well. What characterizes these four cross products? No, not in the... Okay. Give 30 seconds to second years. And then what do they have in common? Yes?
The same result.
They are exactly the same. So you are doing 4 times the very same check, because that is the separating axis, and then you compute the intervals, and the intervals that you compute will be the same, and the result of the check will be exactly the same. Yes, absolutely. A1 and A2, but the direction of A1, B1, C1, and D1, they are the same directions. It doesn't make any sense to test the same direction that many times. How many edge directions does a box have? Yeah.
3.
3 edge directions. So we should just check A1, B1, and F1, right? Only these 3. And the same applies to the other box, right? The directions of the edges are the same. And those directions are the thing that will be used for the determination of the potential separating axis. So, we do 3 cross products, 3 edge cross products versus 3 edges versus 3 edges cross products. So we have gone from 145 tests to seriously, I'm not going forward until everyone hears someone answer. Come on, I heard the right answer. How many tests do we do?
9.
Scream. Yeah, come on, scream. 9! 9, yes. Thank you very much. 3 directions against 3 directions. 9 tests against 144 for the very same result. Just removing the redundancy of the tests. Now you can do the same for the faces actually. That is something you can do, but it's not as dramatic. So yeah, you can do 3 plus, you can do, now you have 6 plus 9, but you can still do just 3 directions versus 3 face directions because the faces have the same direction. So the interval that you compute from this direction and from this direction, well, the interval for the other one is going to be the same. Even though it's going to be, well, the check is going to be upside down, but you can still compute the interval just of the other boxes just once. And so yeah, you can have 3 plus 9. This means that if you do bounding boxes in a smart way, then what results is a truly fast SAT algorithm. So oriented bounding boxes, SAT checks can be really, really, really fast. Well, not as fast as a check between bounding spheres, obviously, but still faster than doing the full SAT checks between arbitrary convex shapes. But does this apply only to boxes, or do you think it could apply to other shapes as well? Yes?
Isn't it that the orientation of the edges are the same, that you can just reduce the color from the
Exactly. Whenever you have 2 parallel edges, you don't need both of them. You only need the unique edge directions. So for every edge, you can do a pre-processing check, and for every edge, you just keep that edge if it's not parallel to another one. Parallel check is that dot products are not exactly one. You cannot remove edges which are almost parallel. They have to give you one, or well, as close to one as you can possibly get. So minus a numerical error. Alright? But in general, and for something like a sphere, at least you will divide at least by 2. For any symmetrical object in general, you will divide by 2 the number of edge checks. And since you do check edges against edges, the less edges you have, the faster your check is going to be. Alright? So with all of this in place, well, you can get to the point where SAT is done as little as possible, and even if you do SAT, you try to take advantage of the symmetries of objects to make sure that SAT itself is as fast as you can. And, well, this gets us very, very close to what a commercial physics engine is actually doing. So, you cannot really optimize that much more besides the computation of the interval, which requires some rather complex pre-processing. Oh yeah, well, yeah, there were some formulas in this lecture, but we're going to skip them. Okay. Oh yeah. All of this is actually, because if you want to optimize the phase checks also, the fact that the interval is the same for 2 opposing directions, you can make that even cheaper, but the difference is not as dramatic. So going from 144 to 9 is really fast. Going from 9 to 7 is less relevant as a game. So it's probably the case that unless you really need to push to squeeze every last bit of performance from what you're doing, having a better middle or broad phase collision detection algorithm is going to be better than spending too much time optimizing the details of the SAT. That's the reason why I'm skimming all of that stuff. Yes?
But a cube with 8 faces, could that be 4?
A cube with 8 faces. I wonder what the 2 excessive faces are.
Well, sorry. Yeah, could it be 3? Like,
yeah, exactly. That is the idea. You can. So the idea is that when you check against a face, so for you can. The idea is that you have these 2 faces, right? And their normals are opposite. But when you take those normals and you take the interval of the projected interval of the points of the other body against those normals, you will get the same minimum and the same maximum, but swapped. So the minimum becomes the maximum and the maximum becomes the minimum because the direction is opposite, but they are the same result. Okay? So you could say, okay, this normal is associated to 2 faces, and you compute the interval just once, and then you check the interval against one face and against the other face, but you do not recompute the interval. That is the idea, yes.
You actually just check if the normal is aligned to the collision normal of the 2 objects, and then only use those faces.
If the normal is aligned with the collision normal of the objects,
like the axis between the centers and
the axis between the centers, that becomes dangerous. Now, this question has actually popped already. The question is, if I give you an answer, I will give you an answer based on intuition. And if there's a single thing that I kind of learned while studying this stuff, is do not trust your intuition for these things. Because it's very
tried this already.
on cubes, but because cubes.
And on pyramids.
Yeah. I wouldn't want it to break some weird cases like very long objects.
Yeah.
Like a very, very, very long object where the mass is only concentrated on an extreme of the object. And it may actually be that you lose some cases. Like a very long pyramid. And if you want to have lots of weight in the pyramid at the base, then I don't know. I get the feeling that if the center of mass is not the same as the center of geometry, then this is going to break miserably, because then you check the center of masses, and yeah. But indeed, in these cases, my gut feeling at this point would be: do not go with your gut feeling. I mean, this applies to lots of things in game development. You can go with gut feeling, but physics is tricky. If you're not 100% certain, don't. Because otherwise you can go crazy by chasing. So it stands to reason. But either test a lot and be ready to actually find negative cases, right? But indeed, I have to find it, but I will investigate a better answer because this kind of got me curious now. All right, so there's two last bits that I wanted to discuss, which are islands and sparse matrices. Now the concept of islands is a concept that is absolutely fundamental. So in my own experiments, this is the single most beneficial thing that I have seen in action. And I've seen that the improvements of having islands versus not having islands are absolutely dramatic. Why? Because not all objects in a physics engine will move at the same time, right? So, alright, I'm not a game designer, but it kind of stands to reason that if everything is moving constantly, then your game is going to be kind of confusing. And in physical reality, you don't have stuff constantly falling over stairs and crumbling to the ground, etc. So physics, as you would expect them, does tend to, physical objects do tend to reach some kind of stable configuration. And the things that move are few, right? Does this correspond to your intuition of roughly what game physics is going to be expected to do?
Yeah, unless you're playing asteroids.
Unless you're playing asteroids, but then the collision system is going to be kind of irrelevant.
Yeah.
Or you can approximate atmosphere collisions.
But then everything is moving.
Yeah, exactly. No, but seriously, think about it. This is something else that one always needs to consider. So what is the domain that you're going to apply this? When you're playing an FPS, physical reactions are usually something that happens, well, not rarely, but not constantly, and for all objects. When you go and you shoot something, you want to see it falling. But it's also kind of something that becomes also a way to give the player feedback about his interactions. Alright? So physics is something that doesn't happen constantly. Now, this said, the idea of islands is that you group objects together in sets of objects which are touching each other now and where some external force is being applied. So you further partition groups of objects into groups that are interacting together, and when an external interaction doesn't happen, like the player doesn't touch them or there is no gravity, they're not moving fast enough, you keep islands and you freeze them. And frozen islands stay out of the physics system until something external wakes them up. Alright? This is the basic intuition. It is actually a very simple object. So it's a way of saying, okay, these objects are touching each other, so they have collisions, etc. So they touch each other and they have collisions. So you might say, okay, so I have to do collision detection, collision response with them. But they're not moving anymore, like a stack of objects. So why would you want to apply collision response to a bunch of objects which are not moving? The collision response is going to do a load of calculations just to determine that no forces are necessary, thank you, right? That's absolutely pointless. Whereas if the player comes in and shoots a box, then of course you want to see stuff blowing up and moving. But unless some external force happens, then as soon as objects remain still, all the objects that are in contact with each other and not subject to an external force become an island, and this island gets removed out of the physics system. You don't process it anymore until some external interaction wakes one of the objects, thus waking the whole island. Alright? Yes?
When you have gravity, does it sort of, because you constantly have a force that's...
Yeah, of course. Constantly you have a force. Now, of course, in this case you have to reason very much. So you cannot really give a general purpose answer. But for example, for gravity, when you find that a stack of boxes is stable, the stack is there, it's not moving anymore,
you'll just freeze them.
Then you freeze them, and forces like gravity do not apply to frozen objects. But of course, when you freeze the objects, you must make sure that the regular force fields are not acting on the objects anymore. Alright?
So you have like sort of a combined threshold of how much force you need?
You have a threshold, no, not of how much force you need, but usually it is a threshold on velocity. So objects which velocity and angular velocity are smaller than a certain threshold go to sleep.
Right.
Right? So the idea is that you partition, the reason why they're called islands is that they're the only objects that can possibly interact with each other, because everything else is separated, and we have found the separation with the previous algorithms. And interactions only happen inside a single island. So, especially collision response will only be done with objects that belong to the same island. Alright? So instead of having just a list of objects, you have a list of islands, and every island contains objects. Of course, you can have islands that merge, because if you have two piles of objects and one falls on top of the other, then of course they will become a single island because now they propagate all forces from all the objects of one island or one falling stack to the other. And you can of course split two islands. I mean, if a bunch of objects get separated from the others, then these are now two islands. Okay? The idea is that you find a way to separate objects and say, okay, these objects are not interacting, they're not subject to external forces, the player is not playing with them, they're still, we don't process them anymore. They don't move, we don't do collision detection of any kind, and especially we don't do collision response, which is rather expensive. Alright, and the way you find the islands is a so-called flood field algorithm. So you know all the pairs of objects which are colliding, and you keep walking through the pairs of objects which are colliding, and you find all the groups of objects which, well, can be reached through a chain of collisions. So, yes, it's just technology once again. So the idea is that you have a chain of collisions that connect these objects, right? So this is an island, and this is going to be another island. Question? Oh, right. And this is going to be another island, and so on. Okay? These are the islands. The islands are groups of objects that may interact with each other. Now, if these objects, these are lots of objects to do collision response on. But if none of them is moving, then the whole island can go to sleep, and so we don't care anymore. And all of a sudden, you stop processing a huge number of objects. And then the physics engine becomes incredibly fast. And it only processes objects for which collision detection and response are actually needed because an external stimulus has happened. So you can have a world full of physics objects, but until the player goes and interacts with them, they cost absolutely nothing. So objects in islands which are put to sleep are just not processed at all. You don't even consider them. You don't think about them. They're out. Right? So of course if you shoot one of these objects, then all the island will be woken up and all the island will be processed. When they go and become still, then the island will be put to sleep again. Right? Is the idea clear? Wonderful. Okay, now, unfortunately, imagine this is the ground. I actually personally went crazy with this one. And you have the following situation. How many islands do you have? How many islands? How many islands do you have? One, exactly. But how many islands would you like to have? 3. Why? Because the ground is not moving. The ground doesn't yet.
Don't you want 4?
No, you just want 3.
4 is also.
How many objects does the first island need to have? This is the first island. How many objects do you want the first island to have?
3. You want to add 4?
How many objects do you want the island to have?
24.
As much as 4.
You want 4. You want 4 because the ground is taking part in the force exchange. The ground is not going to take any force, but it's going to give it back. It's the ground. So if you only have these 3 objects, and yes, I have seen that happen plenty of times, they fall through the ground because the ground is not there. But if you add the ground as an element that can give more objects to the island, then you have these 3 objects in the island, then you add the ground, and then you add all the others. How do we solve this? First of all, is it clear? We want to have 1, 2, 3 islands with 4, 3, and 4 objects, right? Come on, give them a chance.
I have no idea if my solution is correct.
Oh, all right. So come on, what is the point? What do we want to do? Yes.
Island could have like an array, an unlimited array of items, let's say pointers instead of the item themselves. So you can put one item in multiple islands.
Yes, that is good. But which are the particular items that you want to add into multiple islands? Because that is actually the solution. But which are the items that you put into multiple islands? In this case, the floor.
Yeah, floors and buildings.
So these items are called the static items. They do not move, they cannot be moved, they have essentially infinite mass. So the static items can go into multiple islands. Yeah. But there's more. Static items do not connect islands. So when you go through all the objects, you find all the objects that are colliding together, and you keep adding objects whenever you find new ones that are colliding. But when you find a static item, you add it to the island, but you do not go further exploring that item. Alright? So this is the idea. So you build the island only with dynamic objects, and then you add all the static objects which are touching any one of the dynamic ones. Alright? And this way, you can have as many static objects as you want, right? Okay. And one of the most important things is that, yes, the islands will share objects. So the islands will need multiple islands will be able to share the same object, absolutely. So the islands are not the way to represent your objects, because you have duplication, right? The islands are just something additional that you have with pointers to your main objects instead of being the main point of storage. The last bit of optimization is indeed sparse matrices. If you remember, the collision response requires to handle a big matrix of all the contact constraints. The big problem is that this matrix mostly contains zeros. So every line of the matrix contains just 6 numbers which are not zero, followed and preceded by a long list of zeros. So of course, this is kind of pointless, because then when you do a row multiplication, and this row multiplication is mostly doing sums and multiplications with zeros, then you're wasting a lot of time. And if you have lots of if the matrix is very big, then instead of doing very few computations, you're really doing a lot of them. So yes.
Is the matrix for each island or for all the active islands?
One matrix per island. Absolutely, yes, that is the point. So it's already a smaller matrix, but with the projected Gaussian algorithm that we're building, you still have to do this multiplication lots of times, like at least 110 to 100 of times. So you do save a lot, even though the matrix is now much smaller than probably with all the objects. It is still much better to have this process optimized, because it's a small process, but then that runs a lot. So we store every row of the matrix as a list of an integer, which is the index of the column, and a floating point value, which is the non-zero value of that point. So when you do the multiplication between a row of the matrix and a vector, you just you take these values, which are the ones which are not zero, and you just multiply them by the resulting vector. Is this really foreign to you guys? Do you need to do an example? Who wants an example? Raise your hand.
It's free.
Yeah, please.
No, that's money.
Oh. Alright. Okay, so this is your matrix. 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, and 0, 0, 0, 0. Okay? Alright, now, imagine you want to multiply this matrix by a vector. What vector? 1, 1, 1, 1. Right? Very simple multiplication. So, what do we do? Every row is going to be multiplied, is going to be dotted by the vector, right? So we're going to do this row against the vector. So 0 times 1 plus 0 times 1 plus 0 times 1 plus 1 times 1. Okay? This right? Seriously. Matrix by vector multiplication, enthusiasm is required. Okay, now, the point is that this is absolutely unneeded, right?
Yeah.
Right. Okay. So, if you store these values as an array of floating point values, or floating point numbers, then, so the typical code that you would have would be something like this. For e from 0 to n, so sorry, from 0 to n minus 1, for j equal to 0 to square matrix n minus 1, for l equal to sum is equal to 0, for l 0 to n minus 1 once again, sum is incremented by a of ij, oh sorry, il times the vector of L. Alright? Every row is multiplied by with the other by the vector. The problem is that when we go through all the elements, so here, the last 4 here is rather expensive. And even worse. Oh crap, there's 4 too many. Sorry.
Dun, dun, dun.
Yeah. For I equal to 0 to n minus 1. Sum is equal to 0. For j equal to 0 to n minus 1. Sum is incremented by a of ij multiplied by b of j. Oh, this looks better. And then what you do is you say that the result of I is going to be equal to sum. So the result is a vector, and every element of the vector is equal to the multiplication of a row, the ith row of the matrix, by the column, the column of the vector itself. Okay? So the big problem now is that for most j's, ai of j is going to be equal to 0. Almost all the time. How can we do this quicker? For example, if we know the indices of all the elements of A which are not 0, we can skip all the other ones and just consider those values that we care for. So, what we do is we now store the matrix, instead of like this, we store it as this element, which is the element of index 3, has value 1. So we have 3, 1, and this is the only thing that we have in first row. And we have 2, 2, then we have 1, 3. And the last row doesn't have any non-zero elements, so it's actually an empty array. Okay? So at this point, we have the index of an element which is not 0 and the value of that element. Because it's not 0, so we don't know what the value is. So what this turns into is for I that goes from 0 to n minus 1, of course, because we still have to populate all the elements of the results vector. The sum is equal to 0. And now we do for j and the value in a of I. So a of I is an array of pairs, and every pair is going to be made of j and v, the index and the value, right? And this is kind of a softer notation. And then we do that the sum is incremented by v multiplied by, oh sorry, let's call this x by v of j. And then the result of I is going to be equal to the sum. So we are just doing the multiplication by directly going and looking up we use essentially a lookup table over the matrix that tells us the non-zero elements. So this is a very simple thing to build. And this means that if, like in this case, we only have 3 values which are not zero, these are the only multiplications that we will do. Right? We don't even touch the zeros, because that would be pointless. Yeah?
Do you only, for example, if the first row was like 0, 1, 0, 1, would you then just store the first indice and at that point continue on like normal, so also multiply the next one, or do you?
No, you store another entry like this. You would have 1, 1.
Okay. So just.
And they don't even need to be ordered.
Just really only the values.
Just the values which are not zero. Okay. So in the case of our collision response system, we have a matrix with the number of bodies which are colliding multiplied by 6. So this can be and this is for every row, and this is for the number of constraints. So multiplied by the number of constraints k. But what we do is we just have 6 times k values which are different from 0. So instead of doing n times 6 times k, checks multiplications against elements of the vector, we just do 6 times k, which is far, far, far less. Because you can have like tens of constraints and tens of objects. So you are removing a factor that can be rather large, the factor of the number of objects. Alright, so at this point, yes, it is the moment that we always eagerly looking for. Assignment time. So, for this assignment, you should build a broad phase collision detection system, but you can actually pick what you implement. You can do bins, you can do access line bounding boxes, you can do the cheaper test for object-oriented bounding boxes. You can find whatever blend you think is reasonable and interesting to have. It is your choice, right? You don't strictly need to implement them all, and probably if you implement all of these tests, all of these improvements, they are going to fight against each other. So you will ultimately end up with a slower system. So at some point there's going to be an improvement you add which doesn't improve anything and actually makes stuff worse. So look for an interesting balance and just implement that. Reasonably, I would say at least one broad phase method, like the bins. The bins plus the sphere checks is what I would call the minimum for this assignment. But you can be creative, as much as you want.
What's the maximum for the assignment?
Maximum for the assignment.
So what would work, but is probably the most difficult is working properly?
I would say islands, bounding spheres, and either bins or the sweep test. You can have either the bins or the sweep test. If you want to have a very big world, then the sweep test is not going to be enough. But for a medium-sized world, then the sweep test and the bins are less enough. So, some global, very broad phase, then the islands, which are still in the middle range of optimizations, and then something smaller like the bounding sphere to just not jump directly into the SAT test. If you also remove the edges which are parallel to each other, that's very simple to do, and that can give you significant results. Alright? Okay, so, yeah, this is... Oh no, it still took 2 hours. Alright.